Well, welcome everybody to this new session of the Seminar course. Today we're very pleased to have with us Professor Lohner. Who's going to present us his new research in some algorithmic advances for multiphysics boundary conditions and deep neural nets. Reinald is the head of the CFG Center of George Mason University in Virginia, and he received a Master's of Science in Mechanical Engineering in the University of Braunschweig in Germany, and also a PhD and a doctorate in Civil Engineering from the University of Swansea in Wales. His areas of research include numerical methods, solvers, grid generation, parallel computing, visualization, preprocessing, fluid structure interaction, shape and process optimization, and computational crowd dynamics. Reinald, the floor is yours.
Thank you very much. See if I can work this. All right. I'm very pleased to be here again this year. It's always a pleasure to be here. And let's see if I can. The wonders of technology. So I've put together some amalgam of algorithmic advances that we did over the last year. These come from real life runs that we're doing on a daily basis. And some of it may be a little bit technical. I'm going to try to make this as approachable as possible, but other things are very general, particularly the parts at the end. So the first one is this fast identification of separated domains for embedded methods. We all use embedded methods for many years. We typically use them for dirty geometries or cases where we have contact techniques in fluid structure interactions. Since we developed them, most of the users have not switched back to other methods because they always work. So I always put there that sometimes they're overused. So a typical case that appeared in practice was this one here, where we had objects that were moving, and the contact techniques are such. Typically, you have some kind of a spring system, so there's no guarantee that one body does not interpenetrate the other one. And what's happening was that the body was hitting a wall, and now you have a boundary condition here for your body fitted mesh, and this body is squeezing out, and what happens to all the fluid that is inside? The pressure goes up, the temperature goes up, your density goes up, and eventually your time set goes to zero. So we have to find a practical solution to this. So you can see that this technique can lead to these artificial compressions because of the bad boundary conditions of the contact algorithm. And so we need to identify and reset these interior separated domains. Now this can happen every time step, so this is something that you better do fast, because otherwise this will take more than everything else. Okay, so here's a typical case. You have here a high explosive inside. You have a number of spheres outside. The spheres are treated embedded, and over the course of time, the inner circle goes out, hits the other one, and then as you expand, you can see here the regions that have been deactivated and that had to be identified automatically. So how do you do this? Okay, so first technique, a simple advancing front technique. So you build up the connectivities of points that are connected with active edges that are not crossed by a CSD surface, and then you just do a loop over the points, and if the points have not yet marked, you keep adding. So this would be a typical case here. We have two objects, and then we can mark the edges that are crossed. So these are all the deactivated edges, all the red ones. And now we start from one point that is active, and then we go along active edges, looking at all the points that surround them, and we keep adding points. You can see that how this works. Then you have the first domain. Now there will be some points left. These are the points that are inside the objects. And now you go through those. So you start with the next 3 points, and you get the active edges that are connected to it. And you keep going. So that's the second one, the third one, etc., etc. So this is how it looks in Fortran 77, for those that still remember how to do that. So you have a loop over the points, just so you catch all the points. If the point has not been marked, you update the domain, and you go around and advance with layers until you cover everything. And because you have this outer point, loop over the point, you cover all the points of the domain at the end. So this is how you build the list of points, surrounding points that you need. This is again 2 loops over the points. This is classic, so I don't have to go over this again. So the idea is that you have an algorithmic complexity of about 3 times the number of edges, because you have to go over each edge 3 times. And that gives you, on a tetrahedral mesh, about 21 times the number of points. Okay. So it's scalar, mostly. Is the bad part, because now we are running on machines that have up to 128 shared memory threads, and we try to minimize that. So if we can get a technique that is parallel, even though we have many parallel threads, we'll see if we can beat this scalar technique. Okay, so you can partially parallelize that if you start from different points, but of course, depending on the numbering that you have of the points, then this can also work or not. So can we parallelize this? So the idea here is that because of our solvers, getting the minimum of the point surrounding point over edges, we have all of those lists there because that's what we need in order to send fluxes from one point to another. Okay, so this min comparison loop, where we look at a point and then we take the minimum of whatever marker we have at this point and all the neighbors, is something that can be parallelized very well. Okay, so imagine that this can be done 100 times faster than anything scalar that I showed before. Okay, so the idea would be then that we start from the original numbering, and then we just take the minimum of each point and all the surrounding points. And you can see here, after this first pass, these points here now have point number 1, and all of these have been shifted up, and I can do that progressively until I go through the mesh. Well, of course, that depends on the graph depth that you have for your mesh. So this is not something that is going to beat the other algorithm. But if you now remember the points on the other way back, then, for example, for this 1D example, you can get all the points renumbered in one pass. So this is the idea behind this. Okay. So given the current domain number, we can perform a min comparison in parallel. And if the new domain is not equal to the old domain, then we know it's connected. And so we just shrink the number of domains recursively. Okay. And in order to do this well, you have to traverse this from max to min. And you end up with a loop that is something like this. Okay. So you don't have to go into the details. Basically, you start with the highest domain. If the domain is connected to another one, points to another one, you just keep going until you end up with a minimum. You reset all of those, and you do that repeatedly, coming down through the domains. Okay, so that's it. And then you have to do this recursively because in one pass you can't get that. Think of it as lines that you're producing in your mesh. Okay, and so these lines can end up in other lines, and so you need a couple of passes over the mesh in order to get that. Okay, so this is what it looks like. You can see it's not very long. But if you look at the operation count, then the operation count ends up being 17 times the number of points, which was compared to 7, what we had before. It's only a factor of 3 more. All of the operations that you can do here are parallel. Okay, so that's the advantage of doing that. And that's something that actually improves the performance of the code for these complex fluid structure interactions quite a bit. Okay, so this is a typical case here, 230 million elements, about 6,000 pebbles that are floating around there, or objects that are flying. And you can see here, this is in each pass, the number of domains that we identify. So you have 230 million. After one pass, you're down to 148, and then you continue to the remaining domains that you have. Okay, and so if you now look at the number of elements or points that you have, you can see many of these objects only have very few points, and the final domain has this very large number of points, 52 million. Okay, so this is sort of a simple algorithmic idea. It's implemented and running. I'm thinking it can be improved quite a bit more. So I've been, while I was here in Barcelona, I've been trying to code up a couple of things. So I think we can reduce the total count by another factor of 2 before everything is said and done. Okay, so that's the first presentation. Let's see if we can find the second one here. Yeah, okay, so this would be radiation modeling. The idea here is that we're trying to develop a code that can combine the modeling of the temperature in the soil, the modeling of fluid mechanics, and also the modeling of radiation, all in one. Okay, and so what we needed was the radiation modeling, and we had to develop a new code for this. So the most important algorithmic part here that is expensive is obtaining the view factors between one surface and another. Okay, so I just want to cover this a little bit. So we assume that we have a triangulated surface, say a complete city, take Barcelona, so think 1 million up to 10 million triangles. And now we want to get the view factors between these triangles as quickly as possible. Okay, the view factor is given by this integral here, where we have two arbitrary triangles that can see each other, and you have these cosine relationships between them. Okay, so the most CPU intensive part here is trying to see if a triangle can see another triangle. Okay. So the number of phase pairs that you need is n squared. So if you have 1 million, you're already at 10 to the 12. But now if you have to check any other triangle, if that triangle is visible from one triangle to another, it could be another factor of 10 to the 6. Okay, so this makes it impossible to calculate, even if you have a very large machine. Okay, so there's been a major emphasis on efficiency for this. There are many publications, and we tried two techniques. One is the classic octree-based technique, and the second one is a mesh-based traversals. Okay, so the first one is classic. You build an octree. So I've done here in 2D, the surface is the shape that we have, and then you put an octree. It is approximately of the size of the triangles on the fine scale. And now if you want to check if one surface triangle is crossing can see the other one, you just traverse the octree as quickly as possible. The second technique is a mesh-based technique. So the idea is that if we're going to do fluid mechanics on this, we probably have a body-fitted mesh. If we have a body-fitted mesh to generate the coarsest possible volume mesh, is a relatively easy task. Okay, so we assume that we have a mesh, and this mesh typically has twice the number of points that we have on the surface. So it's not a very fine mesh. It's as coarse as it gets. Okay, and then we know for each element where the surface triangle is, and then we can traverse that mesh in a relatively easy manner because we know these are linear elements, and you can come up with a very quick algorithm to traverse the mesh from one side to another. It's just based on shape functions. You just go in time and you take the minimum delta t at the output faces, and that's it. Okay, this technique, which is not, you don't find it in the literature, because in most cases these are algorithms that are developed for games or radiosity or something like that. They assume they don't have a watertight surface, so they cannot build a 3D mesh. But this technique here is 4 times as fast as the other one, at least the way I coded it. Okay, so now if you want to make this fast enough, you also have to take into account that a lot of surfaces will not be able to see other surfaces, so you try to make this hierarchical. Okay? So we typically have bodies, a whole neighborhood or just a building. Bodies have surfaces, surfaces have patches, and then patches are composed of group of triangles or faces. Okay? So, and then we can determine the visibility of surfaces to surfaces or patch to patch in a fast way, because we know what the surface normal or the average surface normal is, and then we can do bounding boxes and try to determine that. Okay, and so you try to avoid the phase pairs that cannot see each other. Okay, and there are a number of sorting factors. So one, for example, is visibility. I know that if this is a flat surface and it has a normal, then everything behind it is invisible. There's no ray that can go from one side to another. Okay, so I can avoid a lot of extra work by doing that. The second one is distance. We know that the view factor diminishes with r squared. Okay, so you can set a cutoff distance. I'll come back to that in a minute. And then the third one is the cost factor. So if I know that this surface here is very far away and this angle here is going to be small, then of course the cost factor is just going to be that small and I can avoid it. Okay, so this is how the loop looks. You do a loop over the patches. Then for each patch, you look at the faces of that patch. And then you check if these patches can see each other because the surfaces can see each other. And then you compute in detail only the face-to-face connectivities where you think you can traverse from one face to another and that they have to see each other. Okay, why would you need patches? Well, think of a million triangles. In the worst case scenario, the radiosity matrix is full. So you have 10 to the 12 real numbers there. Okay, so probably for the calculation of thermal comfort from one building to another, or the person that's walking in, between these two buildings, whether you take the super fine faces or you take something that's a little bit coarser, the result is not going to be very different. But you will be able to do it, because if you really want to do it with 10 to the 12 storage locations, it's going to be expensive. Okay, so the idea is that we would have the data on the body or surface level. Some of the surfaces are large, so that will lead to a loss of accuracy. So you want to split those. And then we also don't want to work face to face, but we want to work patch to patch. Okay. So, and I tried two techniques to take large surfaces and patch them up. One is again the advancing front or greedy, where you just take elements and just agglomerate and you just walk into the surface. And the second one is based on bins. Okay, so here's a couple of test cases. So this is the L-shaped domain. You can see here the surface triangulation, and you can see here a patching that is based on bins. So you can see it has this sort of square shape that you get. Okay. So if you now take the view factors for the patch or for the surface, once you agglomerate the patches, you can get the view factor for the surface. You can see that, of course, here you have higher view factors because these surfaces are closer to each other, these patches are closer to each other, but these are the view factors that you see surface to surface. And those you can compare to analytical solutions, which I'll show in a minute. And this is the CPU time. So you can see it's n squared with a number of faces. So the traversal, the octree traversal or the face traversal, the mesh traversal really doesn't come into account. It's very, very little effect. So this is the meshing. So these are I'm making the mesh finer and finer and finer and finer. This is the exact view factor between the two surfaces, and you can see that this is converging in first order, as you would expect. Okay, so here's a case of the sphere inside the sphere. Again, the analytic solution is known. So the view factor from one to the other should be either 0.75, 0.25, and this one should be 1. So this surface should see the other surface completely. You think about the spheres. And you can see here the number of triangles, and then these are the ones that are traversed and the CPU time. And of course, these traversals from face to face are fully parallel. So the idea is that this group here, this is a fairly large number, so this is the part that you can parallelize. Okay, so now let's look here at a real case. So this would be Oklahoma, downtown, 400,000 faces, about 22,000 surfaces, and about 10,000 patches. Okay, so these are the surfaces numbered, so about 2,000 surfaces. This would be the patches. You can see here these large surfaces here have been patched together. And then this would be the number of visible faces that each face has. Okay, so you can see that the maximum here is about 35,000. So these faces here can see 35,000 other faces that you're trying to compute. This would be the number of faces that you tested in the neighborhood that were crossed by another face that you couldn't get to. Okay, so here you have these ones here that test out, so they would go into all sorts of other directions, about 70,000 of them, but they're not able to go because there's some intersection. Okay, and these would be the view factors for the sun. Should have a video here later. So now the question is your cutoff factors. You think, well, 50 meters is a long distance. Okay, so This is the sum of the view factors. The view factor of 1 means that everything is covered and everything is radiating on you. View factor of 0 is you're on a flat plate and you cannot see anybody. Okay, so you can see here that in this region here, we have very high view factors. Okay, for example, here this would be one phase, one or the other one. Okay, and you can see here now, if we increase from 50 meters, the view factor increase a lot if we go to 100 meters. And then from 100 meters, they still increase if we go to 200. Okay, so the amount of work that you have to do, you have to be careful not to switch off this cutoff factor too soon. As you can see, there are major differences here between these. And you can also see here that if we go to 400, then things sort of even out. The only one at 400 that sees a big difference is this one. It's a very tall building that you see up here. But you can also see the CPU. You know, if you put it at 50, it takes 2 minutes. And then we are up to 400 seconds, 1600, and then more than an hour. Okay, so this is how the sun view factors go along the day. So I've selected here the 21st of June. This is Oklahoma. So we have this automatic that we get for each hour, because some of these thermal runs take several days of real time to run, because you want to set up the cycle. The idea is that if we have a heat wave like the one that we have right now, you want to put water on the streets. So this is what we're trying to simulate at the end. Okay. So the equations now, if you want to get the temperature and the heat fluxes, are these ones here. So for each one of the patches, you have the unknown would be the flux on the patch, and you can see here the temperature that you have. So if you have the temperature prescribed, you can get the flux. Okay, and so this is just one test case here, taken from a textbook. We have 2 adiabatic surfaces here. You have 1000 Kelvin inside here, 400 Kelvin outside with different view factors. And these would be the computed view factors versus the exact ones. You can see they're almost identical. I think the difference is in the third digit. And then this would be the exact versus the radiated heat fluxes that were computed. Don't be fooled by these ones here. They should be 0. It's adiabatic. You can see they're 3 orders of magnitude smaller than these. So this should be 0. And this would be the temperature that you get numerically and the exact one. So again, you're very close. Okay, now you want to couple this to other codes. So here we've coupled this to FE heat, which is a heat conduction code I wrote a couple of years ago. So we have the radiation coupled to the heat, and this would be a simulation of a constant irradiation. And let's see if the movie plays here. So you can see here how the temperature increases, and the number here is the number of days. So I'm computing 24 days. Constant heat doesn't exist in real life, but let's suppose it's the planet that is going around the sun and it's not rotating. It's like the moon going around the Earth, but around the sun. And here you can see the coupling. And so this is again validated, and we tried this against analytical solutions and things of that nature. So we've also coupled this to the flow code now, and we are beginning to do some simulations. Probably the first one will be Zurich, because Zurich is the most digitized city that we are available, that has available data. Okay, so I guess I don't need to summarize this. So we are extending this, of course, also to multispectral analysis. Sometimes for heat, you want to have the long and the short wave radiation separated. Okay, so that's that. And now let's go to this one here. This is the third part that I wanted to cover. And this is the adjoint-based calculation of sensitivity or estimation of sensitivities. This is work that we did for hemodynamics. Just a little bit of background. We have about 3,000 done aneurysms, a database of that. And in all of these cases, we really don't know how well the boundary conditions are. Okay. And what I'm trying to say by that is that we know by now that this has had a huge impact. We can predict the rupture of an aneurysm with an extra accuracy of about 5 to 7% because of CFD. Okay? But if you look, in many cases, we don't know how good or how sensitive the inflow boundary conditions are to the clinical measures that we are measuring in the aneurysm. Okay, so this has been, work of 20 years. Current modus operandi is we set some kind of pipe boundary condition, maybe a Windkessel boundary condition at the exit, and pray for the best. Okay, so is it important? Well, yes, actually it does matter. We had a PhD thesis and a couple of publications 16 years ago, okay? And it is a result that matters, okay? You can see here, if you cut the aneurysm here instead of taking into account the upstream parts, you can get very different boundary conditions, very different flow patterns in there, different shears, different vortical motion, so it does matter. Okay, here's another case. We had a short, so here it was cut in this, instead of taking all of this upper part into consideration, you can see that we have a very different vortex pattern inside the aneurysm. And we know that vortices are important for rupture. And the same here for higher wall shear stress. And here's another case where the original is much, much bigger than the truncated one. So it does matter. And yet here we are 16 years later doing the same thing. Okay, so is there a way that we can get this better? Can we quantify the influence of boundary conditions in geometry? And so option number one is we'll find a different approach. So you make the geometry a little bit bigger, a little bit shorter, and see if your clinical measures inside the aneurysm change. Okay. But of course, if you think about inflow boundary conditions, how many different inflow boundary conditions do you want to put? You just want to accelerate or decelerate, or do you also put vorticity or other things in there? Okay. So the second option would be the adjoint approach, and that is what I want to describe briefly here. Before I go there, an empirical estimation. What is the inflow length of a pipe that we need before we get the Poiseuille boundary condition or the Poiseuille profile? And it turns out it's about 5% of this Reynolds number times the diameter, which for a typical arterial or blood would end up with being about 5 diameters. And we know from the PhD thesis from Castro that you need much more than that, probably 10 to 15. Okay, so if you think about adjoints, you think of an output of clinical relevance, okay, kinetic energy, vorticity, entropy, something like that. And then you have some design or boundary parameters, which could be the geometry or it could be the inflow boundary. And so we want to design, what we want to have is this derivative. What is the derivative of this clinical relevance output with respect to a change of inflow or a change of geometry? And so you get the partial derivative, which is relatively easy in most cases, but then you have the influence here of the change of unknowns if you change the variables. Okay. What comes here as a help is the physics constraint. So imagine that this is Navier-Stokes. Okay, and if you have that, then you can develop these increments here. You know that this delta R has to be equal to 0. Now you pair the terms that depend on delta beta and the ones that determine on the unknowns, and you end up with this term here, which is the important one. So if you can set this one to 0, then there's no influence of the unknowns. Everything is simply a matter of the unknowns that you have. Okay, so if you do this for Navier-Stokes, I've written it in this quasi-incompressible form because it makes the system hyperbolic. It's easier to handle, but it doesn't matter. You can take C to infinity and you get incompressible. And you end up with a PDE for the adjoint, which is a linear system. So you end up with these variables that you have to solve for, and these are the boundary conditions that you have. This is all classic. There's not much new here. What is new is what's coming now. Okay, so you can end up with this adjoint PDE, which as you go with C to infinity, or again, you can keep this term as another P, you end up with the same incompressibility condition that you have for Navier-Stokes, and then you end up with this interesting cross derivative here for the advection and this other part, which is classic. Yeah? But the velocity is going in the other direction. Okay, so if we now look at kinetic energy as our measure of clinical relevance inside the aneurysm. Okay, so we want to compute the influence of the kinetic energy with respect to the inflow velocity inside the aneurysm. Okay. So the clinical measure is in the domain only. It's far away from the boundary. Okay. So the adjoint velocity there is equal to 0. And so we only need to consider the div constraint in R close to the boundary. And you can do that with a small difference in volume approximation. And so this would be the divergence constraint that you get from the boundary. And what is very interesting, what comes out theoretically, is that the derivative of the clinical measure with respect to your inflow velocity turns out to be the adjoint pressure at the inflow, which is a very interesting theoretical result. Okay, so if you can do the adjoint and get the inflow pressure, the adjoint pressure at the inflow, you know what your sensitivity is with respect to velocity. And now let's see what happens if I change the geometry. Okay. So again, the adjoint velocity is 0 there, so all of the terms that have to do with the momentum equation disappear. I only need to consider the div constraint. I can do the same finite volume approximation for that. And I end up with adjoint pressure times the normal derivative of the normal velocity. So if I have a Poiseuille flow, okay, and I change the geometry, nothing is going to happen because the normal derivative of the normal velocity, which is the inflow velocity, is equal to 0, which is what you should have. Think about it. So we verified this, so we take the adjoint for a channel. You can derive an exact solution for that, or in fact, we derived it. So this would be the forward problem. You can see the typical Poiseuille here with the pressure. Now, if you think about the adjoint here, just see if I can bring it back. So you will have a source term here for the adjoint. Where is it? Yeah. So this is the adjoint. So you have a higher force inside the channel because the velocity is higher there than on the boundary. You have still the div constraint, and you have the inflow velocity, which is equal to 0, the adjoint inflow velocity. So what you should end up with is this. Okay, so you're pushing the flow out. Because of incompressibility, there's got to be something that comes in. And so you end up with an inflow here and an outflow there in the adjoint velocity. And the pressure is the same as what you have in the forward problem with the factor. So it's again linear. Okay, so this verifies that the adjoint solver is working. And this would be a typical geometry in a mesh. So this would be the velocity, just a blow up there. And this would be the pressure. And here we have the zone where we have the clinical measure, the kinetic energy. So these are all the points that we consider in our source terms. And this would be the adjoint velocity that you get. And with the adjoint velocity, you also have the pressure. And you can see here, if you had cut it here, you would still see a change in the pressure. So it's not equal to 0 there. Yeah. So you can see that you really had to go quite far away here in order to get the right low sensitivity of your clinical measure to the inflow. Okay, so that's just, I think, some very interesting theoretical results that these derivatives just depend on the adjoint pressure and this normal velocity derivative. And of course, we are trying to extend this to unsteady flows now and also to other clinical measures. So some of them are interesting. If you think about vortex center lines, to take the derivative of that is not so easy. Okay, so final theme is the neural nets. And I'll come back to the other one in a minute, so bear with me. So, as I said in the abstract, no talk in 2022 can be without neural nets. Okay, so here is one. Okay. We've tried parallel deep ResNets for chemically reacting flows. Okay, this is work with the math department and also some of the sponsors there. And so what is the motivation? Well, we do a lot of chemically reacting flows. They take a lot of time. And now we have deep neural nets. So can they help us? Okay. So we've seen a lot of development in the last two decades. They've been extremely successful for sorting, for games, visualization, your translators, your voice recognition in your phone. All of that has neural nets behind it. Okay. So it's and Google has been promoting this incredibly efficiently. Okay? So according to Google, everything can be solved by a neural net. Okay? So it's a new hammer on the shop, in the shop. So how many nails can we find for it? And this is one of the other nails that we can find. Okay, so we have a lot of chemically reacting flows, not only for hypersonic flows, but also if you want to neutralize agents or something like that. It's a system of very stiff ODEs. In many cases, some of the agents that we're dealing with, we have 60 to 80 different species, up to 250 reactions. So not only do you have now the compressible Navier-Stokes equations, which by themselves are expensive for large geometries and cases, but now you have, apart from the 5 unknowns of the Euler equations, you have another 50 or 60 species that you're carrying. And on top of that, you're doing all the chemical reactions on the 50 or 60 species. Okay, so it's no surprise that typically more than 98% of the CPU time is spent in the chemistry. So is there a way that we can get around this? Okay. So can we build a stiff ODE integrator that is based on neural nets that can replace the chemistry that we have? So we want to try to learn dy dt by an exact chemical or stiff ODE solver into something that is replaced by a neural net. So there's been work on deep neural nets. So this is not a very deep one, but it's just to show. Okay, so we typically call width the number of neurons that we have in each layer, depth the number of layers that we have. And what we're trying to determine is the coefficients that we have between these layers. So if you have n by n, it's n squared parameters that we're trying to determine times the number of layers. So don't be fooled when people show you neural nets. It's a lot of parameters that are trying to determine. Very good example. Wait. Okay. So we need to get training data for this. Okay. And so what we did is we ran a lot of cases with the exact chemistry, 0 to cases, and we get the in and output pairs, so X to Z. So this is what happens before the time step. This is what I get after the time step. Okay. And then you try to train the neural net by minimizing the error that you have between the in and output pairs based on the weights and biases that you have in the neural net. Okay. So your weights are the width squared times the depth, and then the biases are the width times the depth. Okay, so if I take a step back and come from finite elements and look at this as an interpolation problem, I can ask myself, am I doing the right thing? Okay, how efficient is really a neural net? Okay. One of the great advances that we did with finite elements is that we use local shape functions. Neural nets use global shape functions. The activation function is 0, and then something at some bias happens, and you either go linear or tan, hyperbolic or whatever. Okay. So we have local versus global, and then the second thing is the efficiency. So let's think in 1D. If I'm thinking of this as an interpolation problem, how many neural nets does it take to just do a linear shape function? Linear finite element shape function. Okay. The answer is I need 3. Okay, because I need 1 to ramp up. That's this one here. That is a bias at x minus 1. This is where I'm starting to ramp up. And I need another one that starts at xi and ramps it down. And then I need one at xi plus 1 that puts it back to level. Okay, so if I want to describe a linear finite element shape function in 1D, I need 3 neurons. If you think about 2 and 3D and 4D and ND, which is people are doing all sorts of input parameters and all sorts of output parameters, the number of neural nets and the number of neurons that I need explodes. Okay, so if you come from finite elements and you think, wow, you guys get magical results with this, then either the problem is very simple or you were very lucky. That's all I can say. Okay? Because from an efficiency point of view, this is not efficient. So the second issue is the quality of the training data. Okay? So is the data sparse? Do I have enough data here? Do I have too much data? Or do I have data that is multi-valued or noisy? These are all things that can happen. And you just throw data at something, you want to have at least some measure of whether this is happening, you're in the dark. Okay? So all of these are not simple to detect in high-dimensional data. Again, people typically don't take 1 or 2 variables that go into the neural net and come out. People take a lot of variables. So we are talking about a very high-dimensional space. And if you only have the data in one corner of that space, that neural net is biased towards that end. In fact, there's a very interesting paper that came out about a month ago on how to fool neural nets for credit cards or for other detection mechanisms in a very simple way. You just train them, just separate the training data and, the results are catastrophic. So the third one is optimization. Okay. It's a difficult optimization problem. Why? Because you have many, many unknowns. It's highly nonlinear. And you have many close, similar solutions that are possible. And this is something that, at least coming from a finite element point of view or from an optimization point of view, is astonishing that nobody has looked at this. Okay? So it's a very rough solution landscape. You think of it, of a sine with a very high frequency, which has all these similar minimum, and you're trying to get to that one. Okay, but it's now one sine on top of another sine on top of another sine. So your optimizer can always end up in some kind of local minimum. Okay, so that's why you have all these atoms and all this stochastic minimization and all the other things that are going on. So what kind of previous work is this based on? Well, there is this so-called physics-informed neural networks, and we've coined another term for this, numerically informed neural networks. Okay, so we are trying to replace the stiff ODE solver by a neural net. So we're not going to be inspired by the physics, we're also going to be inspired by the numerics of a stiff ODE integrator. Okay, and then there have been a couple of papers already published on trying to do chemical reactions with neural nets. Okay, so this is a brief history. We started with H2O2, a very simple reaction, only 8 species, something like that. You download PyTorch or TensorFlow, you press the button, and within half a day you're running. This is one of the magic things about this, and that's why everybody's doing it. It's so easy to download something from the web. You install Python, you press the button, it goes. Okay, so that didn't go anywhere. The optimization was extremely slow, and there were no predictive or reliable results for this. So then we went back to a simple nonlinear 1D ODE, and we trained the neural net, and that worked. Okay. So we noticed, though, that you need a large number of degrees of freedom for a neural net for this to work. So that was a first warning. Second thing was that we improved the optimization. So now instead of taking Adam or one of these other optimizers, we take a BFGS plus a couple of preconditioners. And then the other thing that we also did is just the forward neural net was replaced by a ResNet. Okay, and I'll come to that in a minute. Okay. The third thing that we did is we introduced bias ordering. I'll come to that also in a minute. And then we also split the temperature range. So, first topic, non-uniqueness of neural nets. Simple neural net, fast forward. If you switch this by this, and you switch the weights accordingly, it's the same neural net. For any input that you put in here, you're going to get the same output there. Okay. So if you now think about the optimizer is trying to get all of these weights and is trying to get to an optimum for your training data set. But how many optima are there of this solution? Well, at least n faculty plus n faculty here. Now, so if I have 30 of these per layer, 30 faculty is a very large number. Okay, and now I have for each layer 30 faculty. So if you're not careful, your optimizer is dancing around trying to get one of these 30 faculty equally good solutions. It's a very tough problem for an optimizer. So if you have this, you say, well, wait a minute, can't we do something better? And what we tried to do was we tried to order the biases in a monotonic way in each layer. At least that would give you a unique solution. Okay, so we take the minimum. This is the same statement that we had before, but now we subject this to a monotonically increased bias in each layer. Okay, and that's done via Moreau-Yoshida regularization. It's just you add a regularization term to this error term. Okay, so the second thing is this thing with the deep residual neural nets. Okay, this is some recent work that only started in 2016. So if you think about the usual neural net, it doesn't take this term into account. So it doesn't memorize the old term. And so that can lead to problems like zero gradient, or something can blow up if you have too many layers. If you put this term in here, now this looks like a forward Euler. Okay, so now you can take all of your numerics from ODEs and neural nets, and you can prove things. Okay, so that was a big step. Okay, and that was something that helped a lot. All right, so first of all, this uniqueness. So we're trying to learn just a simple sin x. Okay, and we're trying to learn it with this number of neurons, and we're trying to minimize the error with compared to just simple sin x. Okay, forget, you need 3 neural nets for a linear shape function. Okay, so you have the usual linear increase of a switch function for a neural net. You will need quite a few if you want to get an error to within 1%. Okay, so this is what happens if you do a monotonization. Okay, you can see that this is the optimum without monotonizing. So you can see that these are all over the place, these weights. So the coloring that you see here in the middle is the weights, and these are the biases, and this is the weight. So the biases you can see here are not monotonic. After we do the regularization and use this other algorithm, you can see that these are monotonic. And if you look at the actual solution, this is what you get with the usual one, and this is what you get with the other one. You can see it's much more uniform. You don't get these large errors that you get here. And this is after 10,000 steps of optimizing. So this is not something that happens just like this. So when people claim that they run 30 hours on a GPU, they're basically optimizing. That's where the CPU time goes. Okay, we tried the same for sin x, sin y, and we tried, of course, more layers also for this. And then we tried to visualize what kind of shape functions you get with these neural nets when you look at that. And you can see here, we've numbered them here. Some of them look similar to finite element shape functions, others look quite differently. Yeah. So for example, this could be like a local shape function in one corner, but if you look at this one here, it doesn't look like it. Okay, so then just coming back to the 8 species, simple forward systems did not work. We tried many variations, and about half a year on this, didn't go anywhere. Okay, so then we looked at these parallel ResNets, and we assign. Now what? Severo? I've exceeded my time. Okay, so each we have separate neural nets for each species. Okay, so we have a temperature plus 8 species, so there's 9 loss functions, and so we tried repeatedly the similar structure with FNNs. So these were other researchers that had tried that, and with that you get some better results. So we had 13 data sets. You can see the networks that were trained there, some of the results. I'll be showing the known data sets are in blue. The ResNet, depending on different initializations, either in red or yellow. And these are typical of the results that you get. Okay, some of them are completely off. Other results are getting there. This is a low temperature. And of course, the biggest problem that you have with combustion is when does it initialize? Okay, so it's very, very difficult to get the right initialization for the combustion at low temperatures. If you increase the temperature, now we go to 2200 degrees, things look much better, as you would expect. Okay? Because if you have this Arrhenius factor with 1/T, at 2200, things move a lot faster. Okay, so then we varied the equivalence ratio, bad results. Okay, and then we had a big improvement when we separated the data based on the equivalence ratio. This is what I said before. If you know your physics, you can separate your data, your training data, much better, and then of course you get much better results. Okay, so these were the subsets, and now you can see here for fuel lean, the results are not so good, but as we go to fuel rich, things improve. So again, you can see that at least that the final temperatures are not too far off, but of course the ignition times are still behind. And this would be a fuel-rich case, which of course much better. Okay. So then we went to methane, which is closer to what we have in real life for some of the cases that we're running. We had 15 species in this case. And so we did 16 parallel ResNets here of depth 8 and width 30. Okay, so remember, every one of these is 1,000 parameters. Okay, we have 8 layers, that's 80,000 parameters, and then you multiply that by the species, so you end up with some very large number of degrees of freedom that you're trying to optimize. And also later, if you're trying to compute, if you think about the cost of executing the neural net is also not cheap, because it's not just that you have 128,000 free parameters, it's also that you have some weird functions that are not cheap. Think about a ton H. A ton H on the computer is not one flop. It's expensive. Okay. So this is an initial temperature here of 1250. You can see that most of the parameters are okay, except the initialization time is a little bit off. And then if you go to a higher temperature, things improve. Okay. So in summary, we've implemented these, we've trained them. You saw some of the results. Do I replace Chemkin, my current stiff ODE solver by neural nets at this point? No. Okay, and we cannot really, this is not reliable. Have we made advances towards it? Yes. We are now trying nudging. We're trying some other techniques also to try to also intersperse the stiff ODE solver with, you could think of doing a couple of, expensive ODE steps, stiff ODE solver, and then you do neural nets. So in order to sort of nudge the solution of the neural net into the right place. But of course, then your dream big savings of factors of 10, of course, are gone. So, and so we've also incorporated this sort of this idea that we can read in a neural net and replace the ODE solver in the actual flow solver. Okay, so we've tried a couple of cases with that. We find that they're not reliable, and that's why we don't use it on a daily production basis, but it's in the code. Okay, I think I've exhausted my time. I had one more, which was on actually I developed a series of libraries that tell me in higher dimensions if my training data actually covers the space, if it's multi-valued, it says all these problems that I mentioned before. It's just a library. It's a bit like writing a grid generator. If you don't have a grid generator, you can't do a run in finite elements. Here, I would say, if you don't have this library, don't go and train a neural net because you don't know how good your training data is. And so it's something that you have to do, and well, it's done. Okay, thank you very much.
Thank you very much, Reinald. It was very good presentation and very interesting. We have time for a few questions. Yeah, Carlos.
I would have one per topic, but I spend my token on the hot one, so on the last one. This thing about the biases, let's say, of ordering the biases, are you not limiting the spacing, the solution space in which you seek the solution by doing that?
No.
The point is, if you didn't have the activation function, I would agree with you. But you have an activation, a nonlinear activation function on the output of this.
Yeah, but I mean, it doesn't change. I mean, the minimum, the optimum that you get is the same. All I've done is I've instead of having an infinity or semi-infinite amount of optima, I've constrained it to the one optimum.
But how do you know that you constrained to just the optimum? You took out many of the possible local optimums, but I'm not sure why you can say that the one you retain is the best one.
Well, you can never say that.
Okay, you retained one, that you can say, but maybe one of the ones that you took out was a better one.
No. I mean, there is no difference between the best one that you can get by arbitrarily putting weights or biases and the one that I get. The one that I get for sure is inside that. Because you can, all you're doing is flipping weights and biases.
But if you flip the bias,
Yes.
I mean, let's assume that you keep the same output, so the same weight, and you flip the bias. You may
No. When you flip the two, you're flipping the weight and the bias. Yeah. If you take all of these connections here and the connections of this, and now you flip this to this and this to this, so these connections, then
you're flipping the entire row to understand.
Yeah, sure, yeah, absolutely. It's the same neural net. The output will not change. But for the optimizer, it's much easier.
I understand why for the optimizer it is much easier. I have a hard time in understanding why it is exactly the same, because at the very end, you cannot change the order of the, I mean, here you have a scalar output, but imagine that you have 3 outputs or 2 outputs.
Doesn't matter. You can switch this as much as you want. You know, you can have 3 inputs here. You can switch those.
Oh, sorry, yeah, okay, I read it at the contrary, but okay. No, I'm thinking of the outputs, not of the inputs, because the outputs may be ordered.
If I switch this and this, that output is not going to change.
Oh, that's the loss function your output in there.
Yeah.
But I mean, imagine if your neural network doesn't need to have a single output.
No, you can have many. Yeah. Again, nothing will change.
Okay, I will need some more thinking of this. I read your paper. You have a paper on this, right? Yeah. So you sent it to me last year.
Another question, yeah.
About the first part.
Yes.
When you're looking further away, it gets much more expensive. When you're looking at surfaces that are much further away, because there are many more surfaces.
Yeah.
But you don't need that many surfaces.
Yes.
Okay. So you're doing that. So are you taking less patches, a smaller number of patches when they're further away?
Yeah. Let's say if you think about the city, if I'm going further away, yes, I can make the patches bigger.
Okay.
Yeah.
So,
But inside the city, no, I try to keep them constant.
Okay. But what you really want is to have the same discretization at the angular level.
Yes, that's correct. Okay. But the problem is that you're trying to get from each face to each face.
Mhm.
So yes, you could do a sort of a. I'm standing here and I see that that is very far away. I can do this.
Yeah, I take 1 out of 4 or out 1.
Yeah. Yeah. And then set the same value. No, but I'm not doing that. No. I'm just blindly going at angles and distances.
See, and another question is how you when the surface is not completely smooth, flat,
Yes.
do you just have a tolerance for the
That's
angle?
correct. Yes.
Related to that, the size of the patch is value to be tuned.
Yes. No, the user puts it in. The user says, I want to have a total of 20,000 patches. So it's a fixed number. It's just for speed.
It is not related to the a geometrical feature of
You could relate it. Well, let's see. You compute the total surface that you have, and then you say I want to have 20,000 patches. There may be some surfaces that are smaller than that, so those you don't touch. And you know that surface becomes one patch. So you cannot go below that. Yeah. And even so, for example, if you're going to have a surface that has a certain area, and you know that you were going to get 2 patches, you divide by 2. So you make 2 smaller patches. It doesn't have to be an exact size. And then you end up with some smaller patches in there. So I try to make them as uniform as possible.
Okay.
I was wondering. I forgot the question I had. So, I'll come back to that one.
Okay. Any other question or comment?
I am another curiosity, let's say. I mean, the goal of this is of the thing you presented for the cities to do radiation analysis, some sort of. When you get into, and you have a volume mesh, at that point, doesn't at a certain point start to make sense to use a continuous approach like spherical radiance or?
Yes. The problem is that you have 64 of those.
Yeah, 64 steady state convection problems, let's say.
Well, you're changing the temperature during the day.
Yeah, for every time station, but you also have a n square problem, which you are making faster by the use of a fast multiple method, let's say. What you're doing is like the fast multiple method, similar.
Okay, the solution of the radiation equation is super fast. It's diagonally dominant. You do 50 steps on that, you converge it to 10 to the minus 12. It's astonishingly fast.
But then you can get, I mean, in order to get the
Viewfactors.
Viewfactors,
That you only do once.
but you could do it by using the spherical radiance too, no? I think you can compute the integrals by approximating along the different directions. And essentially for every difference.
Oh, yeah, of course. But then you would need a huge number of rays from each point.
Well,
For some of the.
That's where approximation lays, let's say.
Yeah.
The lesser you put, the worse is the approximation, of course. Yes.
Yeah. And
I'm just asking if the 2 methods do not.
okay. Yes, I'm sure there is some space or some application level where one can win over the other. The thing is that these Viewfactors we compute only once. And then, to do then the radiation calculation for each time step is not, it's incredible. When you think of it, you have a million, you have 10 to the 12 reals that you're multiplying. I mean, today it was a couple of seconds. So in less than a minute, you can get whatever radiation calculation you want. And then this calculation of the sun going around, the Viewfactors for that's again, that's a matter of a second or something, at least for this case of Oklahoma, on a laptop and not on a big machine.
But still you need to store a connectivity matrix, which is sort of sparse. But that's enormous, right?
Yeah. Well, that's why I switched to patches. Yeah, I mean, if I had to store 10 to the 12, that's expensive. Yeah.
There are no more comments or questions. Let's thank the speaker again. See you next seminar after the summer break. See you.